Right. Hi there, folks. Welcome back to our continuation of our discussion on electrochemical cells. So in the last lesson, we discussed a couple different variations of those electrochemical cells and explained how they work and how we can look at different metals and metal solutions and how we can use those to generate electricity. Okay. I've also mentioned, though, that we can use non-metal half cells to also generate electricity, and usually these ones would involve some sort of a inert metal pole or post, as opposed to the anode and cathode that we had in the previous one, where they were the metals that were also in the metal solution. But with the non-metals, that doesn't work out so well. An example that we have here is looking at this reaction where we have our chlorine gas and 2 electrons is going to 2Cl minus. And we're looking at this other reaction where we would take 2H plus 2 electrons to give us H2. Okay, and looking at this, we want to this one here we have going from a 0 charge, getting electrons going to a minus. Okay, so we've got a reduction, but then we've also got this 2H plus with electrons going to the H2. So again, we've got another reduction. So we want to pay attention to where these fall onto our standard reduction potential table. And we notice that the chlorine is much higher up than the hydrogen. So we need to have a reversal of this hydrogen. And what we end up having is this hydrogen undergoes the oxidation while the chlorine maintains that reduction. And so when we combine these two, we can get this chlorine gas plus hydrogen gas going to hydrogen ions and chlorine ions. Okay, so this is just an example of an electrochemical cell that can be done using non-metals. Okay. There are a couple questions there assigned for the textbook. Make sure you try those out to kind of understand how to set up these different electrochemical cells and understand a little bit more about how they work. Okay. Next up, we're going to start talking about standard reduction potentials, right? And that's exactly what that whole table is all about, is that standard reduction potentials. Okay. And we're talking about this, we're talking about potential energy associated with these, or in this case, voltage, okay? The electrical potential that we can get. And these are rated from an arbitrary 0 point. And that 0 point, as I just showed, is this reaction here. We consider this one to have that 0.00 volts, okay? So if we see it higher than this on that table of values, then it would be a positive voltage, and if it's below that, we see a negative voltage. Okay, and we can come back and look at those in a moment. Okay, now these are all the standard reduction potentials that we see. Just pause there to grab our chart here, right? So if we're looking at our chart, hopefully this is close enough that you can all see it. We have our 0 value right here, where we see that 2H plus, okay, 2 electrons going to the H2 gas, as I've written it on the board. And so that is our arbitrary 0 point, right? The potential is based on that 0 point, okay? And that's where we get all of those electric volts, okay, those E naught. Okay, so those E naughts that we see on that chart are actually our E naught for those reductions, okay? And when we're combining these cells, we want to know what is the total potential energy that we can get from that cell, okay? And that's going to equal the electrical potential from the reduction minus the electrical potential for the oxidation reaction, as they are listed on that sheet. I'm going to show you 2 ways that we can add those up. Okay, so let's take a look at this example where we are looking at nickel and iodine. Okay, so I'm just going to look at these few different examples, right? We had this arbitrary 0 point, the 2H plus electrons goes to the hydrogen gas, and we said that that's at that 0 volts. And if we're looking at our potential chart there, the standard reduction potential table of half cells, we notice that if we're above that, we can find this copper 2 plus electrons is a positive 0.34. The iodine gas plus 2 electrons to the 2 iodides is positive 0.54. If we go below the 0 point, we can find lead on there at about a negative 0.13, and we can find this nickel on there at the negative 0.26. So if we're looking at combining our iodine and our nickel in a battery, well then we can look at our E0 cell. Is equal to the E0 for the reduction minus the E0 for the oxidation. Well, we're going to take this iodine from the 0 to the negative 1. This is our E0 reduction. And then this nickel from the 2 plus to the nickel, well, we're going to flip this around to combine with this iodine. And so this is our E0 for the oxidation. So for my E0 for my cell then is going to equal this 0.54 volts minus the negative 0.26 volts. And this gives us a grand total then of 0.54 minus the negative or plus that, so we get a 0.80 volts as the potential from a electrochemical cell made of these two compounds and these two half cells. Okay. Another way we can look at this is if we're using this iodine reaction as is, and that's going to stay as that reduction, and we need this oxidation. So we need to flip this entire reaction. So if we're combining it with this iodine, we're actually going to have this nickel going to the 2 electrons plus the Ni2 plus. And this negative 0.26 volts we have here is based on it going in this order. And that's the way that we have this written out as well. But if I flipped this, I can also look at then, I've got to flip my sign here and get to a positive 0.26. And then now I can just add up my two reactions here. And my electrochemical cell is going to be this iodine gas plus the nickel metal producing 2 iodide ions and the nickel ion. And then I can add up these two voltage and also get to that 0.80 volts, similar to the way that I have it down here. Okay, so just remember, if we're doing it in this method up here, when we flip this reaction, okay, we also got to flip the sign on our E0, or if we're just able to read off our chart and know that we had this E0 for this reaction and our E0 for this reaction, this is the one undergoing oxidation. I'm going to subtract that from my reduction and get it in this way here. Okay, so hopefully that helps out a little bit. Okay. Now, if you look at a cell or you look at the half cells of a reaction and you end up with a positive E0 for the entire cell, then you would have a spontaneous reaction. Okay, we've talked about how we can understand the spontaneous reaction just by looking at where we see the oxidation and reduction half cells on our chart, but we can also look at the overall voltage that we get and understand if it's positive, it's spontaneous; if it's negative, then the reverse reaction would end up being the spontaneous reaction. Okay, so we're going to take a look at another example here, and we're going to look at cobalt 2 plus zinc going to zinc 2 plus and cobalt metal. Okay. So we want to take a look at this and just kind of write out our two reactions. Well, if I'm going from this cobalt 2 plus to regular cobalt metal, that means I have to add in my 2 electrons for this reduction, and then I would have my zinc going to 2 electrons plus my zinc 2 plus for my oxidation reaction. Okay. Now, I want to find these two elements on my chart here. So down here, I've got my zinc 2 plus 2 electrons goes to zinc. I've got, and that has a negative 0.76. However, I've got the reverse reaction, so this is actually going to give me a positive 0.76 volts. I need to find my cobalt on here, and right above here we have our cobalt, plus 2 electrons gives us the cobalt metal. That is the direction we have it on here, and this has a negative 0.28 volts. When I add these two reactions up, I end up with this top reaction. So I can add up these two voltages as they are listed here. And I get an E naught for this cell that is equal to 0.48 volts. Positive E naught, so a spontaneous reaction. We can also take a look at our two reactions that we have here. We have our cobalts up here, and then we have our zinc down here, and we're looking at that reverse. So even just looking at our basic understanding, we've got our reduction above our oxidation. So that would be spontaneous. We can also look at it by looking at our overall E naught for this electrochemical cell. Because it is positive, it is also a spontaneous reaction. Let's take a look at a situation where we would have multiple possible choices to figure out a preferred reaction. All right, so for this example, we're going to look at these three potential reactions here, and this is our multiple options example, and we want to find out what is going to be our spontaneous reactions and what is going to be our preferred reactions. Okay. Now in the notes here, we talk about this preferred reaction after this example, but it really does tie together, so I want to talk about that at the same time. To understand our preferred reaction when we've got multiple options, we're looking for the combination that gives us the highest voltage, okay, the greatest electric potential, and that is the one that's going to be our preferred reaction. So given these three reductions, we need to figure out what is going to be the preferred reaction. Okay, so I'm going to write this out, and I'm going to do a chart. I'm going to do my reduction half cells along the top, and I'm going to do my oxidation half cells down the side. Okay, so looking at this top one, I have 2H plus is going to an H2. I can have my Zn2 plus going to zinc, and I have my I2 going to 2I minus. Those are my three reductions as written over here. Okay. I can also look at those oxidations, which would be the reverse reaction. So I would have my H2 going to my 2H plus. I would have my zinc going to my Zn2 plus, and I would have my 2I minus going to my I2. Okay. These ones here, we're not going to have any reaction. It's the same reaction, just in reverse. Same with the zinc, and then the iodine. Okay, so we're not going to have any reactions there. So, when we are looking at this reaction here, the zinc, going from the zinc 2 plus to the zinc metal, that's a negative 0.76, and we've got the 0 for this hydrogen, so this combination is a negative 0.76. Okay, so this is no reaction. If I looked at the hydrogen gas and my iodine going to the 2I minus, okay, so looking at this as the oxidation and this to the reduction, I end up with this 0.54, so it is spontaneous. Okay. Now, if I took my zinc metal going to my zinc ion, combined with this hydrogen reduction half cell, remember we've flip this around. So we got to flip the sign here. We got a 0.76 with a 0. So we have a positive 0.76. And then this is also spontaneous. Okay, and you can also compare these to the chart and find out which ones are higher and lower to help understand that as well. Okay. Now looking if we had the iodine being reduced and we had the zinc being oxidized, our iodine, we still have the reduction half cell, the 0.54. I'm looking at the oxidation of zinc, means I've got to flip this to be a positive. So that means my combined voltage for the reduction half cell and this oxidation half cell is 1.30. So that makes this one spontaneous. Okay. Now we're going to look at flipping our iodine from being the reduction and looking at the oxidation value of this one. So that would be a negative 0.54. Combined with this reduction of 0, I do have this negative 0.54 volts. So no reaction, negative voltage, no reaction. Okay. And so once again then, if I'm now combining the iodine as an oxidation combined with the zinc. Okay. So if we have this iodine as our oxidation, right, originally that would be a positive 0.54 for the reduction. However, since it's the oxidation, this is a negative 0.54. And combining it with this zinc reduction of a negative 0.76, this cell would give us a negative 1.30 volts, a negative value. So once again, no reaction. So if you compare these different reduction half cells and oxidation half cells to your reduction potential chart and how we determine spontaneous and non-spontaneous, you would see the connections between the ones where we have these positive voltages as being spontaneous and these negative voltages being no reaction. Okay. Now, as we lead forth into this preferred reaction portion, the greatest voltage is going to be our most preferred reaction. So when we're looking at this example, we're only looking at the spontaneous reactions. And so I have this one here with a 0.76, this one here with a 0.54, or this one with a 1.3, 1.3 being the greatest value. This here is the preferred reaction. So we would be looking at our overall preferred reaction being the I2 plus 2 electrons giving us 2I minus being combined with the oxidation of zinc being the Zn giving us the 2 electrons plus the Zn 2 plus. So our overall reaction I2 plus zinc is giving us 2I minus plus the Zn 2 plus, and we get an overall E naught for the cell of 1.30 volts. Okay. So this example helps us understand what is the different voltages, the spontaneous or non-spontaneous reactions from these three options, as well as figuring out what is the preferred reaction by looking at the greatest voltage provided for us, giving us this as the overall E naught. All right, our last example here is if we're looking at a beaker with a whole bunch of stuff in it, we want to know what is going to be the preferred reaction. So in this beaker, we have an iron nail. Okay, so we're going to be looking at pure iron. We have copper wire, so that would again be copper metal, Cu. Magnesium ribbon is that Mg. Okay, dissolved chlorine gas, remember chlorine gas is Cl2. Copper sulfate, this is a fully soluble salt, so we would end up with a Cu2 plus, our SO4 2 minus, and also involved here we've got all of this sitting in water. Okay, and so we want to try and figure out what is our overall reactions that we'd be dealing with to figure out what our preferred reaction is going to be. Okay, so we want to take a look at our chart here. Okay, Now I see my SO4 2-, but that's on the wrong side, right? We want to find an oxidizing agent, or something that's going to undergo reduction, that's going to be higher up than the reverse down here. So another way we can do the preferred reaction is we can look at the voltages, or we can start looking at these different compounds. And as we go down from our oxidizing agents, or the ones that are undergoing reduction, the first one I come across is my Cl2. Okay, that is the highest one on here. So I'm going to be looking at the Cl2 plus 2 electrons, giving us 2 Cl minus. Okay, that is my reduction half cell. Okay, highest value up on the chart, highest voltage, and that one's going to give us an E naught of plus 1.36. Okay. Now, the greatest potential difference that we're going to find is having the highest reduction at the top, and then the lowest possible oxidation down at the bottom. So I'm just looking at my different compounds that I have here on the board, and I want to find, where do I see the first one? And the first one I come across is my magnesium. So I'm going to be looking at that as my oxidation half cell, where my magnesium is going to give us 2 electrons plus Mg2 plus. Now, as a reduction, that has a value of negative 2.37. So based on the way I've got it here, this is going to give us an E naught of positive 2.37, right? The reaction is switched from the reduction as we're given in the chart to an oxidation here. So we take that negative voltage, convert that to a positive, and that allows us to figure out our overall cell. All these other pieces here are just going to be spectators and not involved in the primary reaction. And so if we combine these, we have magnesium metal plus some chlorine gas is going to give us 2 Cl minus plus our Mg2 plus. We can add these two up and we end up with an E naught for the cell equal to 3.71 volts. Okay. That's our preferred reactions. That is the end of our lesson on electrochemical cells. Stay tuned next week for a little bit of practical applications. And that is the end of the course once we finish that little lesson then. All right. Be safe, stay healthy.